This page shows the configuration of the STCMA. The antenna consists of two arrays of plus or minus 45 degrees orientated slot openings on the top of a substrate integrated waveguide, SIW. Each slot opening contains two pin diodes that switch the element between the radiating and non-radiating states. We show that the STCMA can achieve NFF at the fundamental frequency. The STCMA can be viewed as a type of LWA that progressively leaks energy from the waveguide into free space. To realize high directivity pencil beam radiation, the amplitude envelope of an amplitude modulated AM LWA should follow the sinusoidal waveform. To achieve NFF, the amplitude envelope should be generalized into the following equation. To realize Y-polarized radiation, the radiated waves from the two plus or minus 45 degrees orientated slot arrays should have identical amplitude yet 180 degrees phase difference. Therefore, the envelopes for plus or minus 45 degrees polarization should be as follows. The desired amplitude envelopes can be practically implemented by using the time average effect of the spatiotemporal modulation. Here show the corresponding 1-bit STC matrices that describe the slot elements' radiating/non-radiating states in space and time domains. We use FPGA to program the antenna for encoding the operation of meta-atoms and finally realize software-defined automatic NFF scanning. Here we show the measurement results of NFF beam scanning compared with simulations. As observed, measured results are in good agreement with simulated ones. The FWHM of the focusing beam directly determines the resolution of the imaging system. This page shows the configuration of the proposed imaging system. The STCMA and an open-ended waveguide function as the transmitting and receiving antennas, respectively. Every time a new STC matrix is loaded into the Metasurface via FPGA, a corresponding new focusing beam is formed accordingly. In our experiments, 64 states of meta-atoms are designed to generate sequential focusing beams. The required STC matrices are programmed into FPGA and will be loaded upon external triggering to achieve automated beam scanning. The scattering field is utilized as the primary indicator for scene mapping. MATLAB scripts are executed to enable communication and synchronization between the Metasurface and VNA, facilitating the automated and dynamic refreshing of scattering field data for real-time sensing. A conducting rod, 10 mm diameter, 100 mm long, is measured for system calibration. A calibration procedure is carried out to eliminate the effects of scattering from the surroundings and mutual coupling. A compensation model is applied to the calibrated data to counteract the inconsistencies of the emitted beams. A subwavelength conducting rod, oriented parallel to the y-axis, functions as the point scatterer for PSF evaluation. The object is translated along the x-axis in the focal plane, and the corresponding PSFs are measured, respectively. The resolution ranges from 8.94 mm to 13.65 mm. The spatial resolution is constrained by the Rayleigh criterion. Comparison of the theoretical resolutions and measured ones reveals close agreement, demonstrating the capacity of the proposed imager to resolve two objects at distances of 1014 mm at 22.5 GHz. The STCMA is capable of conducting a beam scanning of 64 states within 1 millisecond, facilitating real-time dynamic detection and imaging. The entire imaging process primarily consists of communications among the VNA, STCMA, and MATLAB, as well as data acquisition and post-processing, which consumes approximately 0.2 seconds. The imager enables real-time dynamic 1D imaging at a frame rate of 5 fps. The current imager is confined to conducting 1D imaging solely in the X direction. By integrating the X-axis electronic and Y-axis mechanical scannings, the imager is now equipped to accomplish 2D imaging on the XY plane. A MATLAB script is developed to ensure the fully automated operation of the entire process described above. A test sample has been prepared to validate the imaging performance of this approach. The entire imaging process, including 1472 measurements and data post-processing, can be accomplished within 15 seconds. The imaging result is in good agreement with the ground truth. Given the same configuration, this modality possesses the capability to accomplish rapid imaging and detection in more scenarios, including dielectric objects, hidden targets, and fissures within objects.